Hello students, welcome back. Let us now talk about proof by contradiction. By the way, here's a reminder. This is what we are doing right now. A classification of proofs, direct proof versus indirect proofs. We talked about proof by manipulation and proof by implication. This is what we are doing now, proof by contradiction. How does it work? Let's suppose what we want to prove is false. The conclusion is false, and then we are trying to find some contradiction. Here's a good example. A times B is 0, then either A is 0 or B is 0. By the way, this is called the zero product property, and we discussed it over here. Something times something is 0, then one of those two factors, maybe both, is equal to 0. Okay, how do we prove it? Let's use proof by contradiction. Let's suppose this is false, which means neither is 0. So let's suppose A is non-zero and B is also non-zero. Neither is 0. Then we can start from A times B is equal to 0, and then we can simply divide by A. And what happens here? Divide by A, and 1 over A over A, so that's just B. And then right inside 1 over A times 0, that's just 0, so what do you get? B equal to 0. But that's contradiction because we assumed both A and B are non-zero. So that's how you prove using the proof by contradiction. There goes one example. Too simple? Okay, let's go to a little bit harder example. A is rational and B is irrational, then A plus B is irrational. Prove it. If both are rational numbers, then rational numbers are closed on the addition, multiplication, subtraction, everything. So yeah, sum is rational and the difference is rational. We have everything. But what if one is rational and the other is irrational? We use proof by contradiction. We'll assume A plus B is rational because we have to prove A plus B is irrational. So let's suppose this is false. Assume A plus B is rational, and we're going to go from there. So suppose that A plus B is rational, and then we do a bit of manipulation like this. B is equal to A plus B minus A. Is that clear to everybody? This A and that A cancel each other out, and yeah, B is equal to A plus B minus A. If we write like this, then this becomes a rational number minus rational number, so B is rational. But that's contradiction because we started off as B being irrational. So here goes an example of proof by contradiction. A little bit harder. Okay, how about next example? We did this example in Calculus 2, and usually in Calc 2 I prove it. Let's do it again. This series converges, and that series diverges. Prove that series given by sum diverges. Let's see, if they both converge, then the sum converges. We know that because of the limit rule. But if one of them diverges, then sum has to be divergent. How do we prove that? We do something similar, kind of like that. Suppose that this is false, which means this one converges. And then we do kind of same algebraic manipulation as before, which means something like this. How, and then exactly how do we get contradiction? Okay, I'll stop here. I'll just keep this one up there so that you'll have hint, but no more. Okay, next example. Another example from analysis. This limit exists, converges, and that limit does not exist, diverges. Then limit of product does not exist either, diverges. How do we prove? Again, we do the same thing. Suppose that this is false, and suppose that this converges. And then we can use the limit rule. How do we do that? Well, similar to the previous problems, except that previously we had additions, so we had appropriate addition and subtraction. But this time we have multiplication, so we're going to need appropriate multiplication and division. That's where I'm going to stop. We have enough time for a little bit more examples, so okay, all right. How about these? Prove that the smallest positive real number does not exist. Oh, this is really important example for analysis, but this is not a real analysis class, so let me just skip. How about this one? Okay, let's do it. Another typical example of proof by contradiction is the proof of uniqueness. One and only one. Proof that there is only one additive identity. Let's go all the way back to the property of real numbers here. Okay, algebraic property, here we go. There is additive identity, yes, but there's one and only one, and that's why we can call it 0. If there are more than one identities, then we cannot name it as 0. Let's prove it. How do we do that? Let's suppose there are two, O1 and O2. Let's suppose there are two, O1 and O2. That's identity, and that too is identity. Then we have this kind of computation, and they turn out to be the same, so we have contradiction. But can you actually understand what is going on here? Chances, no, not really, so let's talk about it just a little bit. And this is not directly related to linear algebra. This is more about proof technique. Okay, all right. The first identity, blue equality, is true. Sorry, identity and equality are the same thing, but in this case, I better not use the term identity because I'm using identity for something else. Okay, the first equality, blue equality, is true because O2 is an additive identity. Additive identity times plus something is the same something. So O1 stay the same. Now how about the second equality here? The red equality is true because O1 is additive identity. O2 plus this identity stay the same as O2. So we use both of them. O1 is identity, so we have this red equality. O2 is identity, so we have blue equality. In the end, what do you get? O1 and O2 are the same, and that's contradiction because we assumed they are two different additive identities. Conclusion, there's one and only one additive identity, so we can call it as 0. Now for real number system, this is not really necessary because we know what 0 is. But for more general algebraic structure, this is important. And we're going to start working on it very soon. We're going to talk about 0 vectors soon, and 0 matrices, and then 0 maps and things like those. And all those are related to this uniqueness of additive identity. One and only one additive identity. You can do the same thing for multiplicative identity, but instead, there's one and only one additive inverse for given real number. So name it as minus x. Again, this is not that important because the real number arithmetic is rather trivial. Everybody knows that. But the similar kind of algebraic structures for vectors or matrices or whatever, the same technique applies. Ready? This is harder, much harder. Ready? Okay, let's go. Let's suppose x has two inverses, y1 and y2. And we have this kind of computation. It's a little bit hard to follow, but here it is. y1 is y1 plus 0, and this is in turn y1 plus x plus y2, and y1 plus x plus y2, and 0 plus y2, in the end y2. So what do you get? y1 and y2 are the same, so there's contradiction because we assume there were two different identities, two different inverses, y1 and y2. Now, why do we have all these equalities? Let's follow those one at a time. First, the blue equality. Why is this true? Because 0 is additive identity. So adding identity doesn't change anything, so we have this blue equality. Next, the red equality. y1 stays the same. 0 is equal to x plus y2. y2 is another additive inverse. So additive inverse of x, so this adds up to 0. So that's the red equality. Next, we change the order of addition. That's associativity. The third equality, this green equality, is associative law. Now let's go to this pink. y1 plus x is equal to 0 because y1 is additive inverse. We have two inverses, right? y1 and y2. We use it here. y2 plus x is equal to 0. And y1 plus x is equal to 0, the second one we just used. Finally, brown equality. 0 is additive identity, so adding 0 doesn't change anything, so keeps y2. So that's brown. In the end, what do we get? y1 is equal to y2. They are the same. There goes the contradiction because we assume there were two additive inverses, y1 and y2. Here's the computation, or here is the big equality, and then here are the explanations. Okay, if you can follow all these, then you can feel very good about yourself. If you can't, don't worry too much about these. After a little bit of exposure like this in this class, by the time you take Real Analysis 1, you will be ready.